So how do you even begin to map a system you can't see inside? I mean, what if it's just completely chaotic? Well, today we're going to dive into this really powerful mathematical idea. It's like a brand new language that lets us describe even the most complex systems, turning what looks like total chaos into a map we can actually read.
All right, so here's the game plan. First, we're going to look at how you can observe a system's behavior. Then we'll introduce a simple model. Think of it like a nice straight highway. After that, things get a little messy. We'll hit the city a new challenge. And to deal with that, we'll uncover a new blueprint for complexity. And finally, we'll talk about why this whole thing, why this new kind of map really matters.
Right, so let's tackle that first big question. How do you describe a system when you can't look inside its black box? You can see what goes in, you can see what comes out, but what's happening in the middle is a total mystery. And the secret to figuring it out, well, it's not about prying open the box. It's actually about a really clever shift in how you look at the problem. Okay, first up, observing a system's behavior. It's all about focusing on what a system does. And this is a really simple, but honestly a profound change in thinking. Forget about the internal gears for a second. We're not interested in the how, we're focused on the what. What is it actually doing? You basically become a detective, right? You're just gathering clues from the system's actions to figure out what it's all about. And this entire collection of clues, it has a name. We call it the system's behavior. And it's not just, one single thing that happens. It's the complete set of every single possible path, every trajectory that the system could ever take. It's that whole library of possibilities that really tells you what the system is. All right, so moving on to our second section, the highway, a simple model. This is all based on J.C. Willems' original framework. So to get a grip on this, let's use an analogy. Imagine a really simple, predictable system. Think of it like a perfectly structured highway. You know the kind. Everything flows just right, it follows clear rules, and it's super easy to map out. And this highway analogy just lines up perfectly. So those trajectories we mentioned, that's just the path of an individual car. The system's equations, well, that's just the rules of the road, the speed limit, stay in your lane, that kind of thing. And the whole behavior of the system, that's simply all the possible trips that anyone could ever take on that highway. Simple, right? Okay, on to section 3. The city, a new challenge. Because, let's be real, when does the system get complicated? This is where things get interesting. We run into something called singular systems. So instead of a highway, I want you to picture a chaotic city grid. I'm talking sudden changes, like dead ends, or impulsive movements, where traffic seems to just jump from one street to a completely different one. Or maybe you have these parallel tracks that don't seem to connect. These systems are way, way more unpredictable than our nice, clean highway. And all of a sudden, that simple highway model, it's totally useless. It's just not enough. We've moved from a simple highway to a chaotic city grid. Yeah, the old map is no good when you're dealing with one-way streets, roundabouts, and roads that just end. The old rules just don't work anymore. So that brings us to section 4, the blueprint for complexity. It's all about generalizing this behavioral approach. So what's the fix? Well, the solution required a couple of pretty sophisticated mathematical tools. And what's so cool about it is that it doesn't just throw out the old ideas. Instead, it builds on them, using these really powerful concepts from abstract algebra and geometry. The goal was to create a kind of universal map, one that works for the easy highway and the chaotic city. And it's basically a two-step process. First, they came up with something called abstract linear behaviors. You can think of this as a whole new language, one that's designed to describe all those crazy, complex traffic patterns you see in the city. But, a language isn't a map. So for step 2, they used a geometric tool called coherent sheaves. Now that sounds complicated, but just think of it like this. It's a way to create a unified map of all these patterns. It's the master blueprint. And this is what's so cool. These coherent sheaves, they act like a detailed, unifying map. They describe how all these completely diverse traffic patterns relate to each other. They don't just give you a list of rules. They actually revealed the deep geometric structure that connects every single possible path. It literally turns chaos into something coherent. And this is the big payoff. You get a perfect one-to-one correspondence between the system's behavior and its geometric map. For every single chaotic thing that can happen, there is a precise exact point on this new map. The messy real-world behavior and the clean geometric map, They become two sides of the same coin. They perfectly mirror each other. All right, section 5. Why does this blueprint even matter? I mean, what's the power of having a better map? Well, the bottom line is this. It allows us to analyze and understand a much, much wider class of real-world systems. All those systems that were just too chaotic to model before, the ones that were all city and no highway, we can now finally map them out and study them properly. And this has some really important core applications, things like realization theory, controllability, and observation ability. So realization theory is basically asking, if we have the map of behaviors, can we work backward and build a model of the actual system? Controllability is all about, can we steer this thing where we want it to go? And observation asks, can we figure out what's happening on the inside just by watching it from the outside? These are huge questions in systems theory. So when you step back and look at it, we've gone from a simple highway to a complex city. But now we have a map that works for both. It's this amazing, unified framework that can handle the easy stuff and the really, really hard stuff, all with the same set of tools. And this leaves us with a really fascinating question, doesn't it? Now that we can map pretty much any system, what complex behaviors can we understand next? We have this incredible tool that can take what looks like pure random noise and turn it into a structured, understandable map. So what's next? What other chaotic systems out there, from the wild swings of the stock market to the incredibly intricate dance inside a living cell, what can we finally start to map to understand and maybe, just maybe even navigate?